everyone, and welcome to lesson 21.1. Today's lesson is starting on page 291 in your Springboard textbook, and you will need a pencil and a calculator. On page 291, we see here a quilt block that is made up of a giant square cut into 9 smaller squares, and we're calling it the friendship star. And on this quilt block, notice that some of these smaller squares are then cut up into 2 smaller triangles. So we know, again, that each of these figures, we have these smaller congruent squares to start. And we also then, when we cut those in half, given that all 4 sides of these smaller squares are congruent, we know that the 2 triangles inside are also congruent. And specifically, given the right angles of our squares, right, these triangles, given those right angles, would also apply to them. We would call them right triangles. And because inside of these triangles, these squares here, again, all 4 sides of our square are congruent, which means the 2 legs of our right triangle are congruent, so that it would be isosceles. So, on the next page then, on page 292, we again are talking about these angles. So if you take a moment to kind of draw the right triangles in that we have on the last page, if this is a right angle and we know that these sides are congruent, we know there's 180 degrees total in our triangle, and 90 of them are taken up by the right angle. So we're left with another 90. And then going back to the converse of the isosceles triangle theorem, if this is true, then we know the angles across from the legs are congruent. So each angle would have to be 45 degrees inside of these triangles that we're specifically talking about here. So we call these, if you notice at the top with the lesson name, 45, 45, 90 right triangles. Okay? So now if we look here at the picture of our square block, let's say that this original giant square block was a 9 by 9 square. So this whole thing is 9, and then this is 9, which means each of these smaller squares would be a 3 by 3, right? Each one would be 3 inches. So we would say that the sides of our triangles inside here would be 3 inches, right? It's just 3 all the way around in the squares. Now, going back to Pythagorean theorem, if we're trying to find the length of the hypotenuse C here, we know that C squared equals A squared plus B squared. So C squared equals 18. And if we break this down so that it's a perfect square, we know 18 breaks down to be 9 times 2. And 9's a perfect square. So C is 3 square root, 2. Since this 2 is still left inside the house, right? So the hypotenuse would be 3 square root 2. And if we look at the ratio of the hypotenuse to the leg, it's going to reduce to just be 3 square root 2 divided by 3 is just the square root of 2. Now, what would we say, however, if we change this so that we erase all this, and instead of this being a 9 by 9, this is a 15 by 15 originally? What we would see is each of these would be 5, which means each of our triangle's legs are 5. And again, if we're thinking about Pythagorean theorem, and to solve for that hypotenuse, we know that C squared equals A squared plus B squared. So C squared equals 25 plus 25, which is 50. And we know the square root of 50 then can be 2 times 25, which again breaks down to be 5 and 5. So 5 square root 2. So by now you may start seeing a pattern as we are breaking these down. If our sides are 1 this time, okay, we have noticed they're gotten to this point, these are all 1, so this is 1. And if we're solving for c squared equals 1 squared plus 1 squared, so c squared is 2, so c is just the square root of 2. So square root of 2 divided by 1 is square root of 2. And we start seeing this pattern arise that as we move down here, we know that each of these seem to be this side length x times the square root of 2. We're just multiplying it by the square root of 2 each time. So we have 2 square root 2. And we would have here, since this is something square root 2, this is going to be 6, moving backwards now. Now, the one that would be tricky here to look at is actually this one, because notice there isn't a square root of 2, but all that's missing each time when we're moving backwards is we had to divide away that square root of 2. So we could actually solve if we know the hypotenuse is going to be 4. We know, again, we would just have to divide by the square root of 2 and then rationalize to get this to be 4 square root of 2 over 2, which is just 2 square root of 2. Okay. We'll work more with that in a moment. Okay. So again, square root of 2 seems to be involved that the ratios keep coming out to this value. And basically what we're looking at is if we multiply our leg times the square root of 2, it equals the hypotenuse. Or if we divide the hypotenuse by the square root of 2, then it equals a leg. So basically in a picture, what we're seeing is if our legs are both the same, they're both x, since this is 45 and this is 45, they're the same, we need to multiply that value by the square root of 2 to get the hypotenuse, or divide it away to get the value of these legs. Now, some more examples with this then are on page 293. And again, it goes back to what do we have, okay? So think about in a chart, we have 45, 45, and 90, aka x, and x square root of 2. In this picture, which side are we given? Well, we're given the hypotenuse is 17. And our goal is to just get x by itself, the leg over here. So what we would need to do is take the square root of 17, and divide it by the square root of 2 so we can get x by itself. Now we know we do not want to leave our answer like this. We have to rationalize, like we talked about in the last problem, multiply the top and the bottom by the square root of 2. So we get 17 square root 2 divided by 2, and that doesn't reduce at all, right, as our answer for this missing side. Let's try another one. This time we have the leg, we're looking for the hypotenuse. So as we said before, again, if we look at our little chart here, we actually this time have the x, right? We have the leg. This is a leg. We have this value, so we know that the other leg will also be that value, and to get the 90, we have to take that value and multiply it by the square root of 2 to get the hypotenuse. So 4 square root 10 is our final answer there for the hypotenuse, because the square root of 10 does not break down anymore. Last but not least, we have, again, the hypotenuse given to us on this one. So when we look at our chart, we have the side across from the 90, right? We have the x square root 2 equals 5 square root 12. So to get just x by itself, we have to take 5 square root 12 and divide the square root, this is supposed to be 2 away so that x will be alone. Well, square root of 12 divided by the square root of 2 is the square root of 6. And this would be the length of our two legs here and here. All right, one last example is actually very similar to what we've seen before in some prior examples. And it says we have a square. And we know that all 4 sides of our square are the same size, right? And this is square. And it says the perimeter of this square is 40. Well, remember, with a perimeter of a square, you're adding up all 4 sides of the square, which in this case are the same value. So we know each side would have to be 10 in order for the perimeter to be 40. Now, this question is asking us for the length of the diagonal, which we know the diagonals are the same length in a square from last unit, or from unit 2, part 3. And we're looking for this value here. So we've actually seen this problem a couple times before when we talked about Pythagorean theorem. The nice piece, though, is we now have a shortcut. Instead of having to do Pythagorean theorem, we know that these are the legs, and we know to get our hypotenuse, we just have to take the leg and multiply it by the square root of 2. So as a shortcut, instead of solving Pythagorean theorem, we can say that the diagonal length is the leg times the square root of 2, since that's the hypotenuse. Now, we could always double check that, as we have been doing before. Right? We know that these values would be able to use Pythagorean theorem, since this is a right triangle. So c squared equals 10 squared plus 10 squared. C squared is 200. 10 squared is 100, so add them together. And then when we square root, we know that 2 times 100, which is a perfect square, leaves us with C being 10 square root 2. So again, you get that same answer that we had before. It just took us a lot longer than using our new shortcut. Thanks everyone for watching, and we will work more with these in class.